Welcome back to G Fun Facts Online. For decades, the collective human imagination of spaceflight was dominated by a single, violent image. A rocket aggressively fighting its way out of Earth's gravity, riding a pillar of fire into the blackness of low Earth orbit. From the launch of Sputnik to the assembly of the International Space Station 400 kilometers above our heads, we have truly mastered the shallow end of the cosmic ocean. But as humanity pivots back to the Moon and sets its sights on Mars, the brute force physics of early spaceflight is no longer sufficient. We are entering the era of deep space human exploration, and it is a paradigm shift that requires us to leave behind the relatively simple two-body physics of low Earth orbit and embrace the chaotic, beautiful, and highly efficient invisible architecture of the solar system. At the heart of this new era is the mastery of orbital mechanics beyond the lunar far side. By understanding and utilizing the complex gravitational interplay between the Earth, the Moon, and the Sun, engineers are mapping out a highway system carved entirely out of gravity. This is the story of how we will surf the gravitational contours of deep space to establish a permanent human presence in the cosmos. To go anywhere in deep space, we must first master cislunar space, which is the vast volumetric sphere extending from Earth to just beyond the Moon's orbit. If you look back at the Apollo era, missions relied heavily on brute force to manipulate their trajectories. Apollo spacecraft would fire their massive engines to hit the brakes and drop into low lunar orbit, a path deep within the Moon's gravity well. The problem with this approach is that escaping that well to return home required another massive, fuel-heavy engine burn. Today's Artemis program takes a vastly different, more sophisticated approach. Artemis II, the first crewed mission to return to the lunar vicinity in over 50 years, utilizes a free return trajectory as a primary safety net. The Orion spacecraft will swing around the far side of the Moon, passing roughly 7,500 kilometers beyond the lunar surface. On this path, gravity does all the heavy lifting. The combined pull of the Earth and the Moon naturally bends the spacecraft's track into a massive figure-8 loop that falls back to Earth without requiring a major propulsive maneuver. However, for a sustained, permanent presence in space, a quick loop is not enough. We need a staging ground, a place to build, refuel, and prepare for deeper journeys. This brings us to the Lagrange points. Whenever two massive bodies, like the Earth and the Moon, interact, their combined gravitational pulls and the centrifugal force of an orbiting object create 5 points of equilibrium, known as Lagrange points L1 through L5. If you place a spacecraft at one of these points, it effectively hovers, requiring almost no fuel to stay in place because the gravitational forces perfectly cancel each other out. The Earth-Moon L2 point sits roughly 60,000 kilometers beyond the far side of the Moon. It is a region of profound strategic and scientific value. A station positioned near L2 always faces the lunar far side, providing an unprecedented relay for communication with rovers and astronauts operating in the radio-quiet zone of the Moon, an area entirely shielded from the noisy radio interference of Earth. But hovering exactly at L2 is dynamically unstable, like trying to balance a pencil on its tip. Instead, orbital mechanics gives us a much more elegant solution: the Near-Rectilinear Halo Orbit, or NRHO. This specific orbit is the cornerstone of the Artemis deep space architecture, acting as the home for the Lunar Gateway space station. The Gateway will not orbit the Earth, nor will it strictly orbit the Moon in the traditional, circular sense. Instead, it will be placed in an NRHO, which is a highly eccentric, specialized halo orbit that exists mathematically only in the restricted three-body problem of the Earth, Moon, and spacecraft. To visualize it, imagine a massive, elongated halo hovering vertically over the Moon's poles. The Gateway will fly in a very specific 9-to-2 resonant NRHO, meaning it exactly completes 9 orbits for every 2 lunar months. This path will bring the station as close as 3,000 kilometers from the lunar North Pole and swing it out as far as 70,000 kilometers over the lunar South Pole, taking about 7 days to complete one orbital cycle. Why choose such a bizarre, elliptical path instead of a simple circle? The brilliance of the NRHO lies in its efficiency and accessibility. First, it offers constant communication and power. By flying in that resonance, the orbit ensures that the Gateway almost never passes through the Moon's shadow. This means the station's solar panels are constantly bathed in sunlight, and unlike the Apollo capsules that experienced terrifying communication blackouts when passing behind the Moon, the Gateway's high vantage point ensures an unbroken line of sight to Earth at all times. Second, the orbit has incredibly low station-keeping costs. NASA characterizes low lunar orbit as being stuck deep in a gravity well, whereas an NRHO is balanced delicately on the edge. Because it expertly leverages the gravitational balance of Earth and the Moon, it requires less than 10 meters per second of change in velocity per year to maintain. That is a staggeringly low amount of fuel to keep a massive space station perfectly positioned. Third, it acts as the perfect jumping-off point for the rest of the solar system. Dropping down to the lunar South Pole from the Gateway's closest point requires very little energy, and breaking out of the NRHO entirely into deep space towards Mars is equally efficient. In fact, this orbital path is so important that in 2022, NASA and Advanced Space launched the Capstone mission, a microwave-sized CubeSat, specifically to fly this exact NRHO. It effectively tested the mathematical waters and proved the stability of the orbit before the crewed Gateway modules arrive. By mastering the NRHO, humanity is building an orbital spaceport that rests delicately on the invisible fault lines of gravity. But once we leave the Earth-Moon system, the mechanics of spaceflight change yet again. For decades, interplanetary travel relied on the Hohmann transfer orbit. Proposed by Walter Hohmann in 1925, this method involves an elliptical orbit tangent to both the starting planet and the destination planet, requiring two major engine burns, one to leave and one to arrive. It is the most fuel-efficient two-body transfer, but it is incredibly rigid. It requires precise launch windows that only open every couple of years, and it still requires massive amounts of chemical propellant. But astrodynamicists have realized that the solar system is not a two-body system, it is an n-body system. The gravitational fields of the Sun, the planets, and their dozens of moons all overlap and interact constantly, creating a shifting, invisible topography. By utilizing the complex mathematics of chaos theory and invariant manifolds, scientists have discovered the Interplanetary Transport Network. This is a vast, solar system-wide network of winding tubes that connect the Lagrange points of various planets and moons. A spacecraft carefully injected into one of these invariant manifolds is simply carried along by the natural gravitational currents of the solar system, requiring virtually zero fuel. You could theoretically travel from an Earth-Moon Lagrange point all the way to a Sun-Mars Lagrange point, using only tiny microscopic thruster puffs to navigate the intersections of these gravitational currents. The catch, however, is that it is excruciatingly slow. A transit to Mars on the Interplanetary Transport Network could take decades instead of months. While this makes it entirely impractical for carrying living, breathing humans who are subjected to harsh cosmic radiation and the degrading physical effects of microgravity, it is a revolutionary concept for deep space logistics. Future robotic freighters could use this network to transport heavy, low-value commodities like construction materials, water for radiation shielding, or extracted asteroid regolith to Martian or lunar outposts years in advance of human crews. This creates a highly efficient, slow-moving supply chain that will underpin an entire space-based economy without requiring millions of gallons of rocket fuel. But if the Interplanetary Transport Network is the slow cargo ship of the solar system, how do we get humans to Mars quickly, without bankrupting our resources on massive rockets that must carry their own return fuel? The answer lies in an astrodynamic concept, straight out of science fiction, but entirely grounded in rigorous mathematics: the Mars Cycler. First heavily championed in 1985 by Apollo 11 astronaut Buzz Aldrin, the Aldrin Cycler is a spacecraft placed in a highly specific, highly elliptical Sun-orbiting trajectory. Instead of launching a brand new habitat from Earth to Mars every 2 years, the Cycler functions as a massive, permanently orbiting space station that continuously crosses the orbital paths of both Earth and Mars. Because a Martian year is longer than an Earth year, the synodic period, which is the time it takes for Earth and Mars to align, is about 2.135 Earth years. The Aldrin Cycler makes an eccentric loop around the Sun, swinging past Earth, catching a massive gravity assist, and slingshotting to Mars in about 146 days, or roughly 4.8 months. It then spends 16 months coasting beyond the orbit of Mars before swooping back in to intercept Earth again. The absolute genius of the Cycler concept is that the massive station never stops moving. Once established in its precise orbit, the cycler requires almost zero propulsion, relying entirely on the gravity-assist flybys of the planets to perfectly maintain its momentum forever. This elegantly solves the single biggest problem of deep space human flight: mass. Protecting humans from deadly solar flares and continuous galactic cosmic radiation requires heavy shielding, likely thick layers of water, lining the walls of the spacecraft. Providing artificial gravity to prevent severe muscle and bone atrophy requires massive, spinning centrifuges. Accelerating that kind of incredible mass to Mars and breaking it upon arrival would require a truly impossible amount of chemical fuel. With the cycler, the heavy habitat is already moving at top speed. Astronauts simply launch from Earth in a small, lightweight taxi spacecraft. The taxi fires its engines to match the velocity of the passing cycler, docks with it, and the crew moves out of their cramped quarters into the spacious, heavily shielded habitat for the 5-month cruise. As the cycler zips past Mars, the crew gets back into their taxi, detaches, and uses aerodynamic drag, a process known as aero capture, in the Martian atmosphere to slow down and land on the surface. Meanwhile, the massive cycler habitat simply sails on, empty, looping back toward Earth to pick up the very next crew. To maintain a continuous pipeline, essentially a planetary train service, mission planners propose building multiple cyclers. One up-escalator cycler would handle Earth-to-Mars transit, while a down-escalator cycler on a complementary trajectory would handle the Mars-to-Earth return. This grand infrastructure turns deep space travel from a series of isolated, incredibly risky expeditions into a sustainable, routine interplanetary transit system. Now, while cyclers and halo orbits drastically reduce the need for heavy chemical propellants, maneuvering the initial mass into these trajectories and launching the fast taxis to catch them requires advanced propulsion technologies. Chemical rockets, like the liquid oxygen and hydrogen engines on modern mega-rockets, provide incredibly high thrust. This allows them to escape deep planetary gravity wells quickly, but their efficiency is quite low. Deep space operations require engines that can burn for months or even years. This is where solar electric propulsion comes into play. The Lunar Gateway will rely heavily on its power and propulsion element. Using massive solar arrays, the element generates electricity to ionize xenon gas, accelerating the ions out the back through a powerful magnetic field. While the thrust is tiny, comparable to the weight of a sheet of paper resting on your hand, in the frictionless vacuum of space, this constant gentle push can build up immense speeds over time. This continuous low thrust is exactly what makes maneuvering within the delicate dynamics of a near-rectilinear halo orbit possible. For the fast transit taxis required to catch the speeding Mars cyclers, engineers are revisiting nuclear thermal propulsion. By using a small nuclear fission reactor to heat liquid hydrogen propellant to extreme temperatures and expelling it through a nozzle, this technology offers double the efficiency of the best chemical rockets while still maintaining high thrust. It could shrink Earth-Mars transit times outside of the cycler architecture from 7 months down to under 100 days, drastically reducing the crew's radiation exposure in deep space. Furthermore, orbital mechanics allows us to use pure mathematical trickery to catch the cyclers more efficiently. Astrodynamicists are currently studying a brilliant maneuver called V-infinity leveraging. Instead of launching directly into the cycler's high-speed path, which takes a lot of fuel, a spacecraft can launch into a resonant Earth orbit, coast around the Sun for a year, and perform a relatively small deep space engine burn. When it encounters Earth a second time a year later, it leverages Earth's gravity during the close flyby to massively amplify its velocity. This cosmic trick saves up to 23 metric tons of propellant for a 70 metric ton cycler vehicle. It is the cosmic equivalent of pulling back on a playground swing at just the exact right moment to maximize your height and speed. Of course, understanding the math of deep space orbital mechanics is only half the battle. Integrating the fragile human body into this mathematical framework is the ultimate challenge. The mechanics of the Artemis and Mars cycler architectures are specifically designed around our strict biological limitations. Deep space is a hostile, radioactive ocean. The Earth's magnetic field protects astronauts in low Earth orbit from the worst of solar radiation. But once a spacecraft crosses the lunar orbit, it is fully exposed to the brunt of galactic cosmic rays and entirely unpredictable solar particle events. Spacecraft trajectories must therefore perfectly balance orbital efficiency with human exposure. The Artemis II loop is a carefully choreographed sprint. By swinging quickly around the Moon and returning to Earth in roughly 10 days, the crew minimizes their total time spent in the deep radiation environment. Similarly, the zero-fuel paths of the Interplanetary Transport Network are entirely discarded for crewed missions, simply because a human would absorb a lethal dose of radiation over a multi-year transit. The psychological isolation of deep space also heavily dictates orbital design. The Lunar Gateway's Near-Rectilinear Halo Orbit was selected in large part because it provides an unbroken line of sight to Earth. This means uninterrupted communication, a vital psychological tether for isolated astronauts looking at a home planet that appears no larger than a marble in the black void. Furthermore, the 7-day cadence of the NRHO provides regular, predictable windows for lunar descents and emergency aborts back to Earth. If a sudden medical emergency occurs, the mechanics of the NRHO ensure that the crew is never more than a few days away from a favorable return trajectory, ensuring maximum safety. From the Apollo-era brute force engine burns to the Artemis-era near-rectilinear halo orbits, and looking forward to the immense cyclers and interplanetary transport networks of tomorrow, our fundamental relationship with gravity is evolving. We no longer view gravity merely as a chain holding us down to the dirt. Instead, modern astrodynamics views the solar system as an intricate, undulating topography of peaks, valleys, and invisible currents. The Lagrange points are the safe harbors, the invariant manifolds are the deep ocean currents, and the cycler orbits are the reliable trade winds. The deep space human exploration of the 21st century, beginning right now with the Artemis missions beyond the lunar far side, will not be about conquering space through fire and force. It will be about learning to sail it. By mastering the orbital mechanics of the multibody universe, humanity is finally laying down the permanent, invisible infrastructure required to transform us from a fragile single-planet species into a truly solar system-spanning civilization.